It's time to begin our next session, and it's my great pleasure to announce the next talk. It's an IT talk by Professor Marat Khusniyarov from Friedrich Alexander University in Erlangen-Nuremberg, Germany, and he will speak on molecular switches and sensors based on Valence, Tautomeric, Cobalt, Dioxolenes. Marat, please, the screen is yours.
Thank you very much, Matvey. First of all, I would like to thank all organizers and especially our chairman, Matvey Fedin, for inviting me to give a talk at the MolMag conference. It's my pleasure, as usual, to be with this community. So we are active currently in 4 research areas. Our most advanced topic is photomagnetic materials, where we switch magnetic and other physical properties of molecular metal complexes with light at room temperature. We develop chemical molecular sensors, chemosensors based on redox isomers that respond colorimetrically and magnetically. We construct polytopic ligands for stimuli responsive polymers, and we develop stimuli responsive contrast agents for magnetic resonance imaging. So today I will tell you about all these topics can be combined under the term molecular switches and sensors. And today I will tell you about molecular switches and sensors based on redox isomers. So after wonderful talks given today, I think I don't need to introduce redox isomers, so-called Valence tautomers, to you. What I want to say is that such cobalt dioxolenes, a very special type of redox isomers, this is special because in addition to intramolecular electron transfer between a redox active ligand and a redox active metal, a spin state change occurs simultaneously at the metal ion. So in this case, in principle, we switch between a low spin cobalt-3 or with one ligand radical. This is what we call a weakly paramagnetic state, and a higher spin cobalt-2 with 2 ligand radicals, what we call strongly paramagnetic state. As you can see, very different magnetic, actually optical and other properties of these 2 states make such redox isomers, cobalt dioxolenes, very interesting and very promising for diverse applications. So in Erlangen, we are particularly interested in switching redox isomers with light. A classical approach for photoswitching redox isomers is shown here. So a low spin cobalt-3 state is irradiated into LMCT band, which is followed by a rapid electronic relaxation, giving a metastable transient high spin cobalt-2 state. So this transient state can be stabilized at very low temperatures, and typically one needs to go to liquid helium temperatures. However, at room temperature, this transient state relaxes very rapidly back to the ground low spin state within nanoseconds. Actually, a very similar phenomenon is so-called Liest effect, light-induced excited spin state trapping, is well known in spin crossover research. And also here, a photo-induced state, in this case, a higher spin state, remains stable only at low temperatures, which is not compatible with most applications. One of possible approaches to overcome low temperature limitations of the Liest effect is given by so-called LD-Lisk effect. LD-LISC is ligand-driven light-induced spin change. In this case, a ligand field strength is modulated by a photoreaction, photoisomerization of photochromic ligands. And so light-induced spin crossover becomes possible to achieve at room temperature in principle. Before our works, there was no any efficient LD-LISC spin crossover system available. However, we were inspired by these works, this pioneering works in spin crossover research, and decided to apply a similar approach, for redox isomers. So we introduced photoactive ligands with cis-trans isomerizable units, or with a diuracin capable for photocyclization into, let me say, typical Valence tautomeric metal complexes. So the general idea is the following. By making a photoisomerization of the ligand field strength is changed. And so this can switch the electronic state of the metal complex. And importantly, since a ligand-based photoreaction can be accomplished at room temperature, it becomes possible to switch redox state to switch Valence tautomeric states at room temperature as well. So also we started our research with azo photochromes. For simplicity, I will show you our results and how it works in the case of sterile pyridine derivative. So let us start with thermally induced switching in the solid state and spectroscopic signatures of redox states in this case. So a low spin Cobalt-3 shown in blue, which is observed at low temperatures, shows a low magnetic moment and a nice EPR signal centered at G = 2 due to a ligand pi radical. Okay. A high spin Cobalt-2 state shown in red is observed at higher temperatures, and it shows much higher magnetic moment and is usually EPR silent at elevated temperatures. Another very special signature of Cobalt-3 state in such complexes is ligand-to-ligand intervalence charge transfer band, IVCT band, which is observed here at 2,700 nanometers. So those vertical lines are artifacts due to overtones, vibrational overtones of the solvent. Okay. In our class 3 mixed valence system, donor and acceptor orbitals both are fully delocalized over both ligands, and so you can consider this IVCT band as a very special pi star transition at extremely low energies. So this IVCT band will be very important in the following discussion. So now let's go to solution. We are investigating our complex in solution. The first thing, surprisingly, we observed a partial dissociation of our complex, given a 5-coordinate Cobalt-2 species. And actually, this is responsible for unusually higher thermodynamic parameters obtained from the fit. So initially we were upset because our molecular switch seems to be not particularly stable in solution. However, if you look carefully at this diagram, you might identify an elegant way how to switch between Cobalt-2 and Cobalt-3 states, and namely by adding more ligand into solution. So we took this soup and titrated it with a stearyl pyridine. Upon titration, the IVCT band is increased in intensity, which is, and this IVCT band, one more time, this is a spectroscopic signature of Cobalt-3. And simultaneously, the magnetic moment dropped, also confirming switching to a Cobalt-3 state. So we were able to switch chemically from Cobalt-2 to Cobalt-3 state. So yes, it looks quite simple. However, to our surprise, this effect has not been reported for redox isomers. So actually, we found out this effect by accident, and we called it coordination-induced valence tautomerism, SIFT. One more time, so SIFT, with SIFT, SIFT allows chemical switching of redox isomers at room temperature. However, initially we wanted to switch with light. Yes, we can do it as well. We start with a complex featuring 2 trans isomers of the ligand, and upon UV irradiation at 320 nanometers, the ligands are converted into the corresponding cis isomers. So we are converting trans isomers into cis isomers. Upon this ligand-based photoisomerization, the IVCT band decreased in intensity, the magnetic moment increased, and the EPR signal, which is actually due to Cobalt-3 state, decreased in intensity. So all 3 methods confirm successful switching from Cobalt-3 to Cobalt-2 state. And this is the very first time when redox isomers are switched with light at room temperature. And obviously we can perform our also switching in reverse direction. To achieve this photo switching at room temperature, we used a trick with photochromic ligands. And so we called this new type of switching ligand-driven light-induced valence tautomerism, LD lift. I was very pleased when my PhD student found in a recent review article that our LD Lisk effect has been included into the table comprising the main discoveries in the coordination chemistry-based approach to single molecule magnetism. So now let's go back to SIFT effect and to chemical switching. We thought maybe we can use this liability of monodentate ligands for something else. So maybe to detect or to sense some analytes in solution. Why not? And so here is our approach to molecular sensors, chemosensors based on labile redox isomers. If we start with a high spin Cobalt-2 species and replace the parent ligands L with a strongly coordinating analyte A, then we can expect that the complex will switch to a low spin Cobalt-3 state. On the other hand, if we start with a low spin Cobalt-3 state and manage somehow to replace original ligands with an analyte that produces a weaker ligand field, then the complex should actually switch to a higher spin Cobalt-2 state. So we checked redox isomers available in our lab and found out that the best candidate for sensing applications is again this molecule, this complex with 2 stearyl pyridine ligands. This is because Cobalt-2 and Cobalt-3 states are almost equally populated in solution at room temperature in this case. And this allows to switch in both directions towards Cobalt-2 and towards Cobalt-3 with one molecule. So we took this, this metal complex and titrated it with a simple analyte pyridine. Upon addition of pyridine, the color of solution changed from green to blue. The IVCT, the intensity of the IVCT band increased, confirming the switching to Cobalt-3, and magnetic moment, or in this case, a Chi product, decreased. So both methods confirmed a switching from Cobalt-2 to Cobalt-3 in the presence of pyridine. Upon addition of DMSO, the color of solution changed from green to, let me say, blue-green. And importantly, in this case, IVCT band decreased in intensity. So it gradually disappeared actually. And the Chi product, or effective magnetic moment, increased upon titration. So what we observe here is a switching from Cobalt-3 to Cobalt-2 state confirmed by two methods. And actually, it's what can be expected, since coordinated DMSO should produce a weak ligand field, which should stabilize a high spin Cobalt-2 state. And we actually confirmed this by theoretical calculations and a mass spectrometry. So here, for the first time, molecular Valence Tautomeric metal complex has been successfully used as a chemosensor responding calorimetrically and magnetically. So at this point, I would like to thank my group, our collaborators, and those organizations for providing financial support. Thank you very much for your kind attention. I will be happy to answer your questions, and sorry for giving such a short talk, because just yesterday evening I realized that I was given a slot not for 20 minutes, but for 25 minutes. But at least we have a lot of time, plenty of time for discussions and questions. Thank you.
Yeah, thank you very much. Indeed, we have quite some time for questions. You're welcome to ask. Sergey Weber raises two hands.
Marat, thank you very much for a very nice talk. May I ask you to show slide number 13, where you
Okay.
Yeah, thank you. So you use quite short wavelengths, 320, 270 nanometers, so very short. Few questions. So first one is a technical question. What is the penetration depth? What is the efficiency of switching, I would say, yeah, and which kind of experimental methods you can use to study the influence of such short wavelengths? Yeah, so do you have any problems when you operate these short wavelengths? And another question is, can you change your ligand, or I don't know, something else to go to longer wave numbers, which are much easier to operate? Thank you.
Okay, thank you very much for your questions. About problems with making photochemistry in UV region. Yes, so I cannot provide you with numbers what is the penetration depth, but we are aware of these problems. And so in principle, what we are doing, we are optimizing our setups. So probably the most important thing is that you don't want to have a too concentrated solution. So you need to make this photochemistry So we are irradiating in UV region, and we are irradiating into intense bands, right? So we want to keep our concentration of our solution at minimum, so to allow a nice photochemistry. At the same time, we should be able to detect changes by spectroscopic measurements. So we are providing all numbers regarding concentrations and our setup in our papers, but roughly. So roughly what we are doing, if it's monitoring with electronic absorption spectroscopy, we are probably at 10 to the minus 5 concentrations, and for Evans measurement we need to have more concentrated solutions. It's 10 to the minus 3 probably, but you're welcome to double check in our papers. What kind of setups? Different. We have different setups. One most common setup that we are using, it's just a xenon lamp, 150, with a very large set of filters, UV filters. So it's a bandwidth filters, which cutting particular region in UV region. So I know these filters are not good. They are normally bad because they're not very efficient. But if you go through online shops, and if you're lucky, you're able to find actually efficient UV filters, which allow high intense UV region of a dedicated wavelength to go through. Another photo setup that we have, it's a 1 kilowatt xenon equipped with a monochromator, optimized for UV region and visible region, where we can just adjust exactly the wavelengths and the width, right? It was one question. The second question about what can we do to shift these absorption bands into long wavelength region. There are some strategies known in organic photochromes. It's more common for azo photochromes. You can modify your azo photochrome. So if we go back, azo photochromes, there is so-called push-pull photochromes. When you introduce some electron withdrawing or electron donating, strong electron donating group, I do not remember, then you can shift photoactive band into visible region. But personally, I do not like azo photochromes because the thermal stability of cis isomer is normally very low. So therefore, we stopped using azo photochromes. Currently, we are using, in most cases, we are using Dioxolenes, because Dioxolenes are wonderful. So they are not ideal, but at least the close to isomer, if you're lucky, it survives for some days or some weeks at room temperature. So the strategies are known. So whether you go for Dioxolenes or you modify your azo photochromes. And I have no ideas about sterile pyridine. Sterile pyridines have other problems. The efficiency, you ask about efficiency. The efficiency is not that good, because in case of sterile pyridine, the photoactive bands of the cis isomer and trans isomer, they are overlapping. Therefore, you never can achieve a full switching from one pure state to another pure state. You are switching from one photostationary state to another photostationary state, and this is a problem. And therefore, again, I want to advertise Dioxolenes. With Dioxolenes, it's much less problematic.
Thank you.
We have one question in the chat from Kira Vostrikova. Your complexes are not stable in air. How was the titration organized?
Good question. Sorry. Titrations. We spent quite a lot of time to optimize everything. At the end, it was done in a glove box. So solutions were prepared in a glove box. We can also measure electronic absorption spectra directly in a glove box. And for Evans measurements, yes, so we are preparing our sample in the glove box, take the NMR sample out and then measure it. But it's challenging, right? Actually, just to comment on my own answer, the titration itself, they are not so problematic. So actually, complexes are not dying within seconds in solution in contact with air. It takes some time, but the most challenging experiment was actually switching with pyridine, because pyridine has very low boiling point, and so you want to organize everything. You have your solvent, you have pyridine, everything should be made somehow in a glove box, and this is a challenge.
Okay, thank you very much. Yeah, there are no more questions and we have to move to the next talk. So thank you once again. And the next talk will be given by Fabrice Pointillart from University of Rennes. And he's going to talk on redox and hydromagnetic modulations in lanthanide-based single molecule magnets. Please, Fabrice, go ahead.
Thank you very much, Mr. Chairman. I hope that you can hear me. So first of all, I would like to thank the organizing committee to invite me to give this talk and to give me the opportunity to present some work that we obtained to the University of Rennes. So I should share my screen right now. I hope that you can see my slides. Yes, okay. So yes, today I will talk about redox and hydromagnetic modulation in lanthanide-based single molecule magnets. So after a brief introduction, I will show you 3 different examples of switches, starting with a hydromagnetic switch. Then I will move to redox magnetic switch, and I will finish with a dual redox magnetic and optical switch before concluding about these results. So as you know, single molecule magnets are molecules displaying a bistable magnetic behavior of early molecular origin at low temperature, giving rise to magnetic hysteresis. So we can represent a single molecule magnet with this double energy wheel. Each wheel is characteristic of one orientation of the magnetization. And if you want to reverse the magnetization, you can adapt 2 different processes over the barrier, giving rise to hysteresis, here shown in red, or through the barrier. And in this case, you usually close the hysteresis loop in the applied DC field. So to enter more in details about this processes of relaxation of magnetization, we can write this equation showing you 4 different relaxation processes. The first one is called the well-known Auerbach process, which is a thermally dependent process. In this case, you overcome the energy barrier. As the second one is called quantum tunneling of the magnetization. So it's a thermally independent process, and this is a field-induced. This is a field-dependent process. Sorry, and so you can easily cancel it using an external DC applied field. The third one is a very important process. It's called a Raman process. This is also a thermally dependent process. And it involves a virtual state coming from vibration of both the matrix, so the surrounding of your molecules, but also as a vibrational, the vibration coming from your chemical objects, so molecular vibration. And finally, when you apply an external DC field, you can have also magnetic relaxation through the direct process, which is both thermal and field dependent. So in our group in REN, as many other groups working in the field, we are using the series of lanthanides because they are well known for their strong anisotropy and high magnetic moments. And we can divide this series of lanthanides into subfamilies depending on the electronic distribution of the electron in the 4f orbitals. So oblate family, when the electrons are localized in the plane, or prolate ions, when the electrons are mainly localized along an axis. So if you want to vanish the electronic repulsion between the electrons coming from the metal and the electron coming from the ligand, so if you want to increase the spin-orbit coupling, you have to put the ligand along an axis for the oblate ions, while you have to put the ligand in a plane in case of prolate ion. We can also distinguish along this lanthanide series in function of if you have alpha integer spin or integer spin, called respectively Kramers ions or non-Kramers ions. And regarding crystal field theory, you can have a quantum tunneling of the magnetization in case of non-Kramer ions, why you cannot in case of Kramers ions. Of course, we know that in presence of dipolar interaction, when your molecule is not really isolated from the neighboring molecules, or in presence of hyperthin interaction, you could also observe quantum tunneling of the magnetization in case of Kramer ions. But taking account of the crystal field theory, we choose to work with the 3 dysprosium-3, erbium-3, and ytterbium-3 ions during the 3 following examples that I will show you. In application point of view, the objective, of course, is to decrease the size of the devices for high density data storage and to increase the storage capacity. And in this context, a single molecule magnet could be quite good candidate for conduction application in this point of view. So, of course, this molecular system have some drawbacks, and the main one is the working temperature, so-called blocking temperature, at which you can observe the magnetic stability. So, as you know, this first single molecule magnet was observed for the manganese 2F cluster in 1993, based on the large spin ground state with a blocking temperature of 4K. And 10 years later, Ishikawa published the first lanthanide-based single molecule magnets based on high local symmetry with a blocking temperature of 7K. Almost 10 years later, the introduction of organic radicals allowed to have a strong exchange coupling between the ligand and the metal center, and to increase the blocking temperature up to 14 and then 30 Kelvin. And recently, the magnetic axiality and the design of almost linear mononuclear dysprosium-3 complexes allowed the observation of blocking temperature at liquid nitrogen temperature. So maybe even more challenging is to control, or at least to modulate the single molecule magnet behavior, applying different external stimuli. So we can play with electron to play with the different oxidation state of the metal to achieve the redox magnetic switch. We can play with solvents, coordinated or not to the metal, to achieve solvato-magnetic switch. We can play with light irradiation to induce some chemical change, for example, cyclization of the ligands, to achieve photomagnetic switch, or even play with proton to protonate or deprotonate the ligand and to achieve pH magnetic switch. So the first example that I want to show you today is based on the mononuclear erbium-3 complexes published a few years ago in 2009 by the group of Renaud Coronado. In this complex, the erbium-3 ion is capped by 2 polyoxometallate derivative, and the complex is surrounded by an inorganic network in which you have sodium and water molecules. So what is interesting, if you perform TGA analysis of these complexes, here I show you 3 cycles, the first cycle in black, the second one in pink, and the third cycle in red. You can see that we can remove in a reversible manner the 29 water molecule on the 35, and the desaturation process pass through two steps. You first remove the free and terminal water molecule in blue and green, and then you remove almost all the bridge water molecule in red. So the dehydration and hydration process is reversible. But when you check the structure by PXD pattern, you can see that the starting material is crystalline, but as soon as you heat the sample, you lose the crystallinity of your sample. And even more important, if you check the PXD pattern of the rehydrated sample, the starting rehydrated sample is also crystalline, but clearly the phase is different than the initial compound. So to complete this part, you have a dehydration and hydration process which is reversible, but each time the starting rehydrated sample is in a different phase. So what is the consequence on the magnetic properties? On the top, you have the single molecule magnet behavior published in the paper in 2009. And when you remove the single the water molecule, you lose the single molecule magnet behavior, and you are able to recover it when you rehydrate your sample. You can check also the effect of the removing the water molecule and hydration process by measuring at low temperatures the hysteresis loop, showing that the starting materials of the hydrated sample show a quite nice magnetic B stability. You lose it when you remove the water molecule here in red, and you recover it, but only partially when you rehydrate your sample. You partially recover the magnetic B stability because you have now the same phase after the first cycle of dehydration and hydration process. So to get more information about the structural information along the dehydration process, we perform some periodic DFT calculation. We obtain the optimal structure of the hydrated initial compounds, and then we remove the free and almost all the terminal water molecules, so number of water molecules corresponding to the TGA analysis. Then we remove the remaining terminal water molecule and almost all the bridging water molecule to obtain the dehydrated sample. And if you remove really all the certified water molecule, you destroy your complex. Then, starting from this 4 optimized structure, we perform ab initio calculation to determine the magnetic properties. So first, we determine the orientation of the main component of the magnetic anisotropy, which is quite in agreement with the experimental determination from a single crystal. And we are able to reproduce the chi-T versus T curve as well as the magnetization for both hydrated and dehydrated samples. Then we can analyze the composition of the ground state along the removing the water molecules. And what we can observe is that when we remove the water molecule, you favor the appearance of transverse component of the G tensor. So when you remove the water molecule, you decrease the Ising type character of your magnetic anisotropy. And so you favor the magnetic relaxation through the quantum tunneling of the magnetization. And this is for what you lose the single molecule magnet behavior when you remove the water molecules. So now I will move and switch to the second example. The second example is based on this triad in which we can observe the extended tetratial valence fused with 2 semi-quinone derivatives. So this work was done in collaboration with Vasilij-Kurupatov. We are able to chemically oxidize this semi-quinone triad in the analog quinone triads and reversibly to chemically reduce to recover the starting reduced triad. Then we are able to coordinate the reduced form of the triad with 2 equivalent of 3-hexafluoroacetonate of dysprosium 3 to obtain this dinuclear complex. We can do the same starting from the oxidized triad now to obtain the analog oxidized dinuclear complex. And more interesting is that we can oxidize or reduce directly the triad starting from the coordination complexes. we are also able to obtain single crystals of both reduced and oxidized form. Here I show you the X-ray structure of the reduced form of the dinuclear complex of dysprosium 3, in which we can see that the triad is not planar because you have no aromaticity and locally fully delocalized system. But after oxidation, we get a planar triad, and we can see that the oxidation induces the coordination of one water molecule on each dysprosium 3 center. This additional water molecule have consequence in the packing. So on the left, you have the packing, crystal packing of the reduced form, showing in the appearance some isolated complexes. While for the oxidized form, we have formation of pseudo chain due to the hydrogen bond of the water molecules and forming some pseudo dimer of dysprosium 3 with quite short distances between the two dysprosium 3 centers. So this is different in the crystal packing have consequence in the K-T versus T curve. So in blue, you have the reduced form of the complex showing at low temperature some intermolecular dipolar interaction. The intensity of this interaction was determined by ab initio calculation, while is not the case in for the oxidized dinuclear complex. You can also determine the ground state as well as the energy gap for the two systems. And you can see that the reduced complex is more display a more Ising character for the magnetic anisotropy than the oxidized one. So we are able also to determine the orientation of the anisotropy axis, and you can see that upon oxidation, we have a rotation of this main component, the G zeta component of a G factor. And all these results that we obtained by ab initio calculation were confined by experimental torque measurements thanks collaboration with Lorenzo Tesi from the University of Florence. So we check the frequency dependence of the magnetic susceptibility and zero applied magnetic field, showing that the two compounds behave as a single molecule magnet. But clearly, the reduced compounds display a much slower magnetic relaxation than the oxidized analog. We can also apply an external DC field of 1200 Ørsted in order to remove the quantum tuning of the magnetization, and so slowing down the magnetic relaxation for the two compounds. But also in this case, the reduced form of the dinuclear complex display much lower magnetic relaxation than the oxidized one. We are able to quantitatively analyze these dynamic properties, plotting the thermal dependence of the relaxation time, and we are able to fit this thermal dependence using Orbach and QTM mechanism in case of the oxidized dinuclear complexes, and Orbach only mechanism under applied fields, while for the reduced form, we had a Raman component. Okay, so I will switch to the last example, which is simply the ytterbium-3 analog of the second one, to have a redox magnetic and optical switch. So the reduced form of the ytterbium analog is isostructural to the dysprosium one, but upon oxidation, we observe different dinuclear complexes. Because now we have the additional coordination of the water molecule because the ytterbium-3 ion is much smaller than the dysprosium one. So we first dependence of the magnetic susceptibility, showing that none of these two complexes behave as a single molecule magnets. Nevertheless, as soon as you apply an external DC field, you can observe appearance of an out-of-phase component of the magnetic susceptibility, sign of slow magnetic relaxation. And when you increase the value of your DC field, you have a shift of the maximal 2K to higher frequencies, sign of presence of direct mechanism. Then we try to quantitatively interpret this data, but in case of the oxidized analog of the ytterbium-3 ions, since the maxima is almost out from your experimental frequency window, we are able to do it only in case of the reduced one. So here I show you the frequency dependence of the magnetic susceptibility under an applied DC field of 800 Ørsted in case of the reduced form of the ytterbium analog. We plot the thermal dependence of the reaction time, and we're able to reproduce and to fit this curve, this data, using a combination of both Orbach and direct process. But as you can observe, you have a very weak effective energy barrier, and so that is a strong indication that the main magnetic process for magnetic relaxation is a direct process, and we can confirm that by optical properties. So on the top, I show you the absorption properties for the two reduced and oxidized analog of the ytterbium, respectively in green and red. What is important is the redshift of the charge transfer band, localized here at low energy upon oxidation. In fact, when you irradiate at the same energy these two compounds, in case of the reduced one in green, we have a very nice ytterbium-3 centered emission. And from the two highest energy band, we can determine the energy barrier, which is close to 300 wave number, so much higher than the effective barrier determined from the dynamic magnetic properties, which confirms that the Orbach process is almost not involved in the magnetic relaxation. And when you oxidize your compound, we switch off the emission of the ytterbium-3 ion. So to explain why we have this optical switch, we draw the so-called Jablonski diagram. On the left in green for the reduced form of our complex, on the right in red for the oxidized form. And what is important is the energy of this charge transfer band, so the SOMO-LUMO charge transfer band, which is higher in energy than the emission state of our ytterbium-3 ions. So we can have an effective energy transfer and then emission of our ytterbium-3 ion as experimentally observed. While upon oxidation, the charge transfer band is redshift. So now the HOMO-LUMO charge transfer band, the energy of this HOMO-LUMO charge transfer band is almost the same that our energy of the two F5 states. And so we have now an effective back energy transfer. And so we switch off the emission of our ytterbium-3 ion. So it's almost time for me to conclude. So during the first example, I show you that we can switch off and on the magnetic B stability depending on the hydration or dehydration process in mononuclear erbium-3 polyoxometallite derivatives. I show you that we can have similar switch on off of the magnetic B stability playing with the oxidation state of our bridging triad. And for the ytterbium analog, I show you that we can have a dual redox magnetic and optical switch. I would like, of course, thanks all the people involved in this project. So Vincent Dorsey for the X-ray diffraction on single crystal, Olivier Maury for the optical properties, Kevin Bernot for the TGA and PXRD analysis, Boris Legenik and Vincent Motico for the DFT and ab initio calculation, Vyacheslav Kuropatev for the nice collaborations that we have using this triad involving extended Valence, Lorenzo Tesi from University of Florence for the cantilever torque measurements, all the members of my group at the University of Rennes 1 and the Institution for the Monnaies, NRS, French Agency, University of Rennes 1, and the ERC for funding, and you for your kind attention.
Thank you very much. There are already, there is at least one question from Nikolai Yefimov. Please go ahead.
Yes, thank you for interesting presentation. And Fabrice, it's look like you use, in a case of erbium, you used isotope 166. Why did you do it?
Yes, this is another part of the work that I didn't show today. In fact, in this work, we perform also isotopic enrichments, playing with natural isotope, but also pure isotope 166 and 167 to remove the hyperfine interaction. Because in this original paper and one year later, they show that when they remove the hyperfine interaction using pure isotope, they observe counterintuitive trends. I mean, when they remove the hyperfine interaction, the pure isotope displayed a much faster relaxation of the magnetization. So we want to verify that because we play a lot with isotope in case of dysprosium-3 and ytterbium-3 based single molecule magnets, and in all these cases, usually when we remove hyperfine interaction, you should decrease, let's say, the probability to have quantum tunneling of the magnetization, and so you should slowing down the magnetic relaxation. So here, it's just because I don't show you the part about isotopic enrichment.
Thank you. And I have another question, if it's possible. In AC data for dysprosium complexes for oxidized form, you show what it looks like. The frequency dependencies are non-symmetrical. Yes, this one non-symmetrical. Yes. And is it two different environment of dysprosium, or what's happened? And if yes, why it's only it's symmetrical for non-oxidized form?
Okay, this is a good remark. Probably in case of the reduced form, we have only one Gaussian, and so it means that you have really only one environment or only one symmetry, while it's quite large. So if you look at the alpha values, the alpha value is quite far from zero. So alpha value equal to zero, it means that you have only one relaxation time. So only one molecular object. So probably it could be associated to different, very small distortion around the dysprosium, and probably a distribution of different compounds. Why is like not different compound, different environment for the same compounds? Is probably because we chemically oxidize the reduced form, and then I isolate one by one the single crystals that we obtain of the oxidized form. But the conversion is not 100%. So probably the crystals are maybe dirty, and so you have something very similar, but not exactly the same. So the AC data are very, very sensitive to any small change. I don't want to say symmetry around the dysprosium 3, but more a change of electronic distribution around the dysprosium 3.
Thank you, Fabrice. Thank you.
Okay, thank you very much. This was a very interesting talk. Indeed, but we have to move to the next one. And the next lecture will be given by Professor Yulia Nelyubina from Nesmyanov Institute of Organoelement Compounds, Moscow. Yulia, please go ahead. And
can you hear me?
Yes. Yeah. Yes, we hear you and we see your presentation. Perfect.
Okay, thank you for your feedback. First of all, I would like to thank the organizers for providing me this opportunity to present my results in the field of the spin crossover. This morning, Professor Halcrow, in his nice talk, argued that spin crossover is a crystal engineering problem. But before we are trying to control the packing of the molecules, which is a real challenge, and sometimes took some luck to be successful, we need to understand what is going on with your system on the molecular level. Or to put this into nice words, you should be able to do a molecular design of your spin crossover complexes. And this is what we are doing in my lab in the last few years. As a family of the complexes that we try to do molecular design, we have chosen these iron 2 complexes with these bis-pyrazolyl pyridine ligands. So the idea was that you took the ligand, you try to functionalize it into different positions, and so you're able to control the spin crossover behavior. And this idea was seen quite achievable at the time, because as you can see here, the system that we have chosen is a sister system to the bis-pyrazolyl pyridine or 1-BPP ligands that Professor Halcrow was talking about this morning. And that those guys, they started so well that the principle of the molecular design of this kind of complexes are well elaborated. In a nutshell, depending on the position that you want to functionalize, you can control the spin state of the metal ion like so. For example, if you target the first position that is closest to the coordinated nitrogen atom, then putting some substituents into this position will give you entirely high spin complexes. And this is what we don't want in our research. Of course, we want to have the spin crossover and to somehow control it by shifting the temperatures of the spin crossover to lower or ideally to higher temperatures. And when you're talking about the complexes of 1-BPP ligands, depending on the position, you can either use electron withdrawing groups or electron donating groups, so you can play with your temperatures and shift it to low temperatures. And if you take the functional groups with opposite electronic effects, then you have an opposite effect, so that the spin crossover curve shifts to higher temperatures. And this is what we want in the spin crossover research for the applications of the spin crossover complexes, for example, as molecular sensors. So the correlations quite nicely found for this kind of complexes that we expected to be the same for our system. But there are some reports in the literature that it may be in fact be quite opposite. So, and the reason why there is still a controversy in literature about the effects of different substituents on the spin state is that these 3-BPP ligands, they have these NH groups. And these NH groups, they just love to form hydrogen bonds with the counter ions or with even solvent molecules. So the spin state of the iron metal is very environment dependent. And this dependence is very hard to predict and therefore to control. So the molecular design here is not an option. And this was the first hint that maybe we choose the wrong system for the molecular design. And the second hint was that, I'm sorry, something happened. I cannot switch. Oh, yeah, no problem at all. And the second hint was that if you put any substituent to this nitrogen atom, you get entirely high spin complexes. But we decided to still give it a try, and for this we of course needed to be clever in the choice of the substituent to be put into this position, so that it will not prohibit a spin crossover from occurring. And if we're lucky, when we can use the same. I'm sorry, I have some problems from my part. I cannot switch my slides. Oh, there, yeah. And then if you have this coligand that allows you to perform a molecular design, so then you can choose other substituents to put into the ligand into different positions and therefore control the spin state of a metal ion. As we are talking about the molecular design, when they will need to have some kind of a technique that allows us to probe the spin state with no interference from crystal packing effects, because they sometimes can block the spin crossover from occurring in the solid state. And as such technique, we as chemists decide to use the nuclear magnetic resonance spectroscopy. In a nutshell, by using a very simple 2-volt tube device setup, you can get the result nearly the same as from the simple DC magnetometry measurements, but for the liquid state. And so these are the problems that we needed to solve in our research, and at the same time, it is an outlook of my talk. Of course, the first step, that is the most important step towards the molecular design, is to find some kind of a substituent to be put instead of to block these NH groups. And as such substituent, we decided to try the phenyl group. Why phenyl group? Well, the problem is that when you put a bulky group into this position close to the nitrogen atom, these groups, they try to avoid sterical clashes with the second ligand in the complex, thus effectively stabilizing the high spin state. But the phenyl groups, they can rotate to better adapt themselves to the geometry of the complex. And so we expected that these kind of complexes decorated with the phenyl groups will be finally able to undergo a spin crossover. Unfortunately, this wasn't the case after we have measured probed the spin state of this complex in a solution, where it turned out to be entirely high spin. And this is despite the fact that indeed we can see that the phenyl groups are rotated relative to the paraxylene plane, as you can see from this nice picture from X-ray diffraction. And exactly the same kind of the geometry with the rotated phenyl rings remains in the solution, as we have found, as follows from results of the quantum chemical calculations. But if you go to the hypothetic low spin state, you can see here that the two aromatic groups are nearly perpendicular to each other. And going from the left side to the right side, it takes some energy. There is some energy penalty for the rotation of the phenyl ring relative to the paraxylene ring, because upon the rotation, you lose the conjugation between these two aromatic fragments. So it turned out that the phenyl group is still not a good choice for the substituent to be put into this position, and still will be able to observe a spin crossover. But the reason here is the ability of this phenyl group to rotate. But we can rather easily control the energetics of this rotation, for example, by using bulky substituents that we can put into ortho positions of this phenyl ring. And this is what we have done. We synthesized a series of such complexes when the substituents X were fluorine and chlorine atoms or methyl and methyl groups. They have different electronic characteristics, and most important, they are of different sizes. And we expected to finally induce a spin crossover in this kind of otherwise high spin complexes, in contrast to the parent complex that was high spin in the solution. And luckily, we indeed observed that 3 out of these 4 new complexes undergo a spin crossover in a solution. And this result can again be rationalized by using the energetics of the rotation of these two aromatic fragments. This time, thanks to these bulky substituents, for example, like a chlorine atom, the complex prefer to have these two aromatic fragments to be in a perpendicular configuration, which is typical of the low spin state. And by doing so, we were able to stabilize the low spin state of the complexes so that a spin crossover was finally observed in the solution. But if you look closer at the midpoint temperatures for the 3 spin crossover active complexes, you can see that their order do not follow the order that we expected based on the volumes of these substituents. And the reason behind this may be seen from these X-ray diffraction pictures. Here, the ethyl group is anisotropic, and so it has in the complex the terminal methyl group rotated away from the metal center. So probably when we went to estimate the steric effect of this ethyl group on the spin crossover behavior, we should better use a volume that is close to the methylene group. And in this case, we have a nice order of, we mirror the order of the midpoint temperatures of in these spin crossover complexes. But what would happen if we take even bigger substituents into the ortho positions of a phenylene? We decided to check the result by using a bromine substituents and even larger isopropyl group. Unfortunately, the isopropyl group turned out to be too big for the second ligand to enter the coordination sphere of the metal ion. So the complex of the required ratio 2:1 was not observed. Luckily, we had no problems whatsoever with the ion-2 complex of the bromine substituent. Unfortunately, it turned out to be again high spin in the solution. And this time, this result cannot be rationalized by talking about the energy penalty, or better put it, stabilization by rotation. As in this case, the bulky bromine atoms, they also force the complex to have these two aromatic fragments in the perpendicular configuration. On the other hand, this result is quite what you can expect from the general knowledge in the field of spin crossover, which is if you put a bulky substituent into this position, you would have an entirely high spin complex. And this is in contrast to our observation of the spin crossover upon going from smaller fluorine atom to bigger chlorine atom or methyl and ethyl groups. So the major step that we did, the step number 1, was to devise this kind of a substituent that you can put this close to the coordinating nitrogen atom and still be able to observe a spin crossover. So clearly, if we have this coligand, we can now try to control the spin state of the metal ion, the spin crossover behavior, by putting different substituents into the same position of the free BP ligand as it was targeted by, in the case of the complex of 1 BPP ligand. And as a co-ligand to do this research, we decided to take the complex with the chlorine-containing ligand, as it has the midpoint temperatures that was quite high. It was around the 0 centigrade. So the first strategy that we decided to use is to functionalize the pyrazolyl ring, I'm sorry. And to do so, we decided to put 5 different substituents into this position that had different electronic characteristics and different sizes. So what we hope to achieve is to observe a spin crossover in all of these complexes at different temperatures. And this is exactly what we have observed when they synthesized the series of the complexes and probed its spin state in a solution. From this data, we can obtain the midpoint temperatures of the spin crossover that varies in a rather wide range. And after we try to plot these midpoint temperatures against the Hammett constant sigma m that quantifies the electronic effects of substituents in this position of the pyrazolyl ring, we were able to observe let's say a positive correlation between these two parameters. And looking at this correlation, you should better take an electron withdrawing group if you want to shift the spin crossover closer to the room temperature. I should note that this correlation is quite the opposite to the correlation what was found for the ion-2 complexes in 1 BPP. But it agreed nicely with some reports on exactly the same effect of the electronic effects of the substituents into this position that were previously observed for the complexes with unsubstituted triple ligands. I mean the one that had these dangling NH groups. To pinpoint the exact reasons behind this difference between the 1-BPP and 3-BPP ligands, we still need to carry out quantum chemical calculations that are underway in our group. But based on the experimental results that we obtained by using NMR spectroscopy, you can be sure, or you can have an idea that if you want to shift the spin crossover to higher temperatures, you better use an electron withdrawing group into this position. If you somehow want to do exactly the opposite, you better choose, for example, a thread-butyl, electron donating thread-butyl group. So it was the step number 2 towards our result, or towards the molecular design of spin crossover complexes by using this kind of ligands. And this should be true for the para position of the pyridine ring. At least it was previously observed for the complexes with isomeric 1-BPP ligands and other pyridine-based ligands as well. To push this hypothesis, we decided to synthesize just recently this kind of ligand that had an electron withdrawing para-cyanophenyl group in the para position of the pyridine ring of our 3-BPP ligand. So what we expected to do is that we can effectively shift the temperature of the spin crossover from 0 centigrade to closer to the room temperature. And as a reference to again test our idea about the effect of the electronic characteristics of the substituents in the paraxylyl ring, we synthesized this sister complex that had in the paraxylyl ring electron donating thread-butyl groups instead of electron accepting hydroxyl groups. And both of these complexes again undergo a spin crossover in a solution. And if you quantify the midpoint temperatures of this spin crossover and compare them, you can immediately see the effect of the substitution in the paraxylyl ring. And it is exactly the same that we have established for the series for the previous series of complexes. And if you compare this kind of ligands with the unsubstituted ligand, you can see the expected result of the electronic influence of the substituent at the para position of the pyridine ring. Here you can see that taking electron withdrawing group, we were able to shift the midpoint temperature by 30 degrees close to the room temperature. And so to formulate an alternative approach to control the spin state of the metal ion, you can see on the slide in the schematic form that if you, for example, choose an electron withdrawing substituent inputted into the para position of the pyridine ring, you will indeed be able to shift the spin crossover towards higher temperatures. So this is the third step that we took to go towards the molecular design of our complexes. And among our many different complexes that we have obtained so far, one of them that combine electron withdrawing groups in both positions of the 3-BPP ligand undergo a spin crossover that is nicely centered around room temperature. So this is what we want for the practical application. And for example, if we take some kind of a substituent of the similar, that have similar electronic effects like para-cyanophenyl group, but the one that can produce complexes that are soluble in aqueous solution. And if you keep these OH groups that you can protonate or deprotonate, then hopefully you can get a water-soluble complex with a spin crossover centered around room temperature. So it can be, for example, used in diagnostics of cancer, like pH sensors for diagnostics by magnetic resonance imaging. So to conclude my talk, this is the recipe for the successful molecular design of spin crossover complexes by using this kind of ligands that, to say the truth, are not very good for this task. But to do so, you just need 3 key ingredients: the substituent, the green one of our design, and different electron withdrawing groups in all these positions of a 3BP ligand. Well, this recipe still needs some tweaking, but so far it produced us with the series of spin crossover complexes that are otherwise spin crossover inactive, and even one of them being a rare example of spin crossover complexes that undergo spin crossover around the room temperature. So at the end, I would like to thank all the people that joined me in this quest for molecular design of spin crossover complexes, the Russian Science Foundation for funding this project, and all of you for your kind attention. Thank you.
Thank you very much, Yulia. I see at least one question from Professor Marat Khusniyarov. Please, Marat.
Okay. Thank you very much for a great talk, Yulia. So you mentioned actually at the end of your talk about water solubility. Just to clarify, have you already obtained some complexes that are water soluble and that do not decompose in water?
Yes, we just obtained the complex that had a pyridine substituent in the para position of the pyridine, so somewhere here. And this complex is indeed water soluble, and it stays stable in aqueous solutions. In fact, the stability in aqueous solutions is an advantage of using complexes of 3BPP in contrast to complexes of 1BPP.
Yes, I know.
Yeah, so yes, we just obtained it, and we even measured the probe. We also probed the spin state of this complex, and it features a spin crossover around I think it's near 40 degrees centigrade. So it's nearly what we want to have to use them like as a pH sensor.
I see. Great. How do you check the stability of the complex in water solution? Electrochemical spectroscopy.
NMR. We usually use NMR. Yes.
Okay. Thank you.
Okay. Next question is from Sergey Weber.
Yulia, thank you very much for the interesting talk. My question is related to biological application. You mentioned that in principle, spin crossover compounds could be quite efficient in NMR tomography. And do you know maybe about your compounds or in principle similar works about applicability of spin crossover compounds? Are they safe for living beings or for animals? So, okay, you studied stability in a water solution, but for example, in the blood, the stability can be maybe better or maybe lower. So do you know about literature concerning this? Thank you.
Well, there's some research on the possibility to use the spin crossover complexes as pH sensors, as I mentioned. But the research were just like in regular solutions. No one went beyond in vitro studies. So no one really tested the biological application, the safety, the toxicity of the spin crossover complexes. But I think it's not good to have the derivative of pyridine in your body, but it's even worse to have a cancer. And about the solubility, and we only measured, because we just obtained these complexes of pyridine, we only measured in water. And of course, we're planning to use different solutions to test how it behaves in other solvents.
And do you plan to go in this direction, biological applications, I mean?
Yes, I think so, because we have these complexes that show the spin crossover at the ambient temperature. Because if you have your spin crossover at 180 Kelvin, you cannot use it in a living body. But it just they're like beginning, I hope, of the next direction of our research.
Thank you very much.
Oh, another question from Professor Malcolm Halcrow. Please, Malcolm.
Hi, very nice to hear you talk about this work. The complexes you have with OH groups on the pyrosols look interesting. I mean, as you said, it's well known that the NH groups of those pyrosols are very sensitive to hydrogen bonding, which has a large effect on the spin states of the ion complexes. So are those OH groups also important? Do they hydrogen bond very well? And are those complexes sensitive to that if you measure them in different solvents, perhaps?
Thank you for the good question. In fact, we try to use different solvents to probe the spin state of different complexes. And for this guy here, we used 2 different solvents, and the midpoint temperature was like, the difference was like 5 Kelvin or something like this. So the difference is not so large.
Okay. That's interesting. It's a bit further away from the metal, I guess.
Yeah. I it's raising, yeah.
And just lastly, I mean, we only published 1 paper on this, but we did look at 3 BPPs with some amino substituents in the 5 position at 1 point where your OHs are. And we found that some of those complexes were often air sensitive, I think, because the NH2 groups on substituents on the pyrosols, they deprotonated quite easily.
Yes.
So is this a problem that you encountered?
Well, in fact, just recently, again, we obtained a complex that has, instead of the OH groups, it has the aniline derivative, aniline substituent. Mm-hmm. But we again measured it by using this NMR technique, and we didn't see problems with it if you use some kind of, for example, acidic solution and so on. In fact, I think that this is not like a problem, but like a possibility to try to deprotonate the OH groups, the NH groups, and try to control the spin state of the ion to ion even further.
Sure. Okay, thank you.
Thank you.
Okay, thank you, Yulia. Thank you all. And we continue to the last talk of this session, which will be given by Dr. Kseniya Maryunina from International Tomography Center, and she will talk on nitroxide-substituted Cymantren and Cyrhetren synthesis, structure, magnetic and electrochemical properties. Please, Kseniya, the screen is yours.
Hello, dear participants. At first, I would like to say a lot of thanks to organizing committee for their effort to organize so wonderful conference. They got us opportunity to be here together, and it's very great honor for me to represent from behalf of myself and my colleagues the study of first examples of nitroxide-substituted Cymantren and Cyrhetren. At first, I would like to say to you that I am very lucky and very happy scientist. I can work and I can combine so amazing building blocks like metallogens and nitroxides. So both of them are very amazing. From one hand, sandwich compounds are magically attractive. So not from only from point of view of their functional properties, they just aesthetically, from aesthetical point of view. From other hand, the nitroxide radicals are the most accessible story how to stabilize wild, very dangerous free radicals and how to stabilize unpaired electron in organic substance. So both classes of these objects have high potential for application. Nowadays, the most significant interest of scientists focuses on the search of new compounds exhibiting some pharmacological activity. And Cymantren and Cyrhetren, along with Ferrocin, are the most stable sandwich compounds under ambient conditions. And we decided to attach to Cymantren and Cyrhetren derivatives diamethylene nitroxide substituent. So from one point of view, the robust configuration of cyclopentadienyl ligand and the low spin configuration of D6 metallocenter provide high kinetical inertness of these complexes. Also, it's quite easy to do functionalization of these compounds. Also, we have a lot of possibility because this fragment has very small size and can mimic the benzoyl ring in some targeting receptors. And we have also opportunities for radiological treatment with rhenium isotopes or do some photodynamic therapy or cell releasing therapy. So these compounds are very attractive in design of drugs for theranostics. So that means that we can do in the same compound therapy and diagnostic. Despite the high potential of Cyrhetren for using in chemotherapy, in photodynamic therapy, or in radiological treatment with isotopes of rhenium, for diagnostics now we can use mostly single photon emission computer tomography with help of technetium-99m agents. Another promising approach from our point of view is to attach to half sandwich compound something paramagnetic, for example, nitrogen nitroxide radicals, and use it as a contrast agent in magnetic resonance imaging. So in this case, we can combine both profits from these compounds in one molecule. It will be kinetically stable, this part, and also metallocene part, and also it will have effective contrast properties because of nitroxide. Also, we have some mimicry properties of metallocene, offered to be on school label, and also we have possibility to do some radiological treatment or some photodynamic therapy, and this would be very promising approach to synthesize, and this prompts us to synthesize some nitroxide-substituted Cymantren and Cyrhetren. Cymantren and Cyrhetren derivatives were synthesized in usual way by Wolfgang method. So the nitroxide, nitrogen nitroxide and immunonitroxides with manganese and rhenium. Sorry, here should be only both metals. Are kinetically stable and both in the solid state and in the solutions. So we can easily handle with them, and however, we got several trials and errors to develop the method of synthesis. For example, at this step, we had to use only dry ethanol to do very good condensation. And concerning the Cymantren derivatives, we need to protect them from visible light. So I had very interesting experience in both in half light and to protect every my flasks with foil. Fortunately, all these compounds are quite stable, so we can do a lot of studies with them. So we studied electrochemistry, APR spectra, and also we got a lot of structural data and studied magnetical properties of these nitrogen nitroxide and amino nitroxide derivatives. So the EPR spectroscopy study have shown that obtained Cymantren derivatives are typical nitrogen nitroxides and amino nitroxides radical. They show typical lines in the spectra and usual splitting parameter at the nitrogen atoms. The shape of EPR spectra for Cyrhetren derivatives a little bit more complex due to the high natural isotopic hydrophile splitting at the rhenium nucleus. So, but the splitting at the nitrogen nucleus is almost the same like at for Cymantren compounds and for other nitrogen nitroxides and amino nitroxides radicals. According to the cycle Tautomeric data, nitrogen nitroxide undergoes one electron reversible oxidation to stable oxoammonium cation. The amino nitroxides oxidize irreversibly. The potential is higher than for nitrogen nitroxides that should be associated with a higher electron transfer energy and low stability of the oxidation product, which can react with other parts in solutions, some moieties, and so we have not here only electron process, we have also some chemical processes. Both nitrogen nitroxides and amino nitroxides irreversibly reduce it. That is typical for most compounds containing nitroxide fragment due to the high basicity of this oxoammonium anion. So Cyrhetren derivatives have shown very similar electrochemical behavior. So external electrochemical impact on amino nitroxides and nitrogen nitroxides, Cymantren and Cyrhetren derivatives induce electron transfer only in nitroxide moiety, and while their metallocene part moiety remains unchanged. So we grow crystals of all Cymantren and Cyrhetren nitrogen nitroxides and amino nitroxides, and X-ray diffraction study showed that the bond lengths in coordination sphere of metal centers and N groups bond lengths are in good agreement with previously reported data for Cymantren and Cyrhetren derivatives. So the coordination sphere of atom is unchanged after attachment of a nitroxide fragment, and also nitroxide fragment is almost the same. It is actually a nitroxide fragment for all these compounds. So we have now unique objects where in one molecule we have together half sandwich and nitroxide building blocks. According from the results of DFT calculations, the spin density it was found is mostly concentrated to imidazoline, to this part of imidazoline rings. So it has very small value at the rhenium center. And the value at the rhenium center has very good agreement with obtained constant or hyperfine splitting at the rhenium nucleus, so big at the in case of nitrogen nitroxide and smaller at the amino nitroxide. But in total, the electron density at rhenium center is very small, very important because mostly electron density is concentrated at imidazoline ring, like usual for nitrogen nitroxides and amino nitroxides. And it's very important because also we every time had the question of the possibility of intramolecular charge transfer and the existence of spin isomers of these compounds. Because if spin isomers exist, So it's not good because our compounds would be not stable. Like for example, in this case, so they have some charge transfer from one molecule to another in solution, from Cyrhetren to semi-phenol moiety. And also, I can show you another example from Cyrhetren moiety to some this molecule. And also the same story, not the same, but very similar story. We have then manganese metallocentres reduce the nitroyl nitroxides, and we have something like charge transfer effect for manganese nitroxide species. So Vitaly Morozov performed DFT calculations to calculate is it possible to get some spin isomers or charge transfer, and it was shown that nearest energy spin isomer are above the ground state of the initial nitroxide, about 70 kilocalorie per mole or for nitroyl nitroxide and 90 kilocalorie per mole for imino nitroxide. This is the performed for rhenium compound. So we have very interesting spin isomer where only one electron pair is unpaired, and nitroxide moiety is the same like for initial compound. If we try to transfer this electron to nitroxide fragment, so to obtain this kind of rhenium-2 complex with amino anion, the energy of this spin isomer is much higher than for previous described one. But this energy also is very big, is too large, and so now we are sure that we have not any spin isomers that can be temperature induced or light induced for our compounds. That is very good because our compound is very stable, and we can prepare very good drugs on their basis. So also I got back to this slide. Because of spin density is mostly concentrated on nitroxide fragment and nitroxide group, in crystal structure of these compounds, we consider mostly the contacts of this nitroxide group with high spin density to neighboring molecules. That is very important for organization of effective exchange interaction channels and for describing magnetic properties. So in crystal structure of nitroyl nitroxide Cyrhetren, or Cymantren, we can observe the dimers with pi contacts between cyclopentadienyl rings and quite short distances between, here it's shown nitroxide group. And these dimers, they are shown in green, are connected in chains with help of hydrogen bond that the nitroxide groups is connected with hydrogen atom of cyclopentadienyl ring. So for imino nitroxide Cymantren compound, we have very similar structure. With one exception, that here it's amino nitroxide. We have contact only between nitrogen atoms of imino nitroxide fragment. If you consider magnetic properties of this compound, you can see that here in exchange interactions for nitroyl nitroxide compound is much bigger than for amino nitroxide compound, and also because here we have much smaller contact, much shorter between two nitroxide groups. Here between two imine atoms or to nitrogen atoms of this context is much bigger, and overlapping of magnetic orbitals is not so effective. So DFT calculation shown that these exchange interactions in dimers are much more effective than exchange interactions in chains. And also we had tried to calculate exchange interactions for amino nitroxide complex, but they are too weak to performing this calculation with good quality. So concerning the complex Cyrhetren nitroxide derivatives, it was shown that Cyrhetren nitroxide derivatives can be crystallized in three polymorphic modifications. At first, at fast precipitation, we obtain crystals of polymorphic modification 1. Then, if you will allow to stay under solution, the crystals of these polymorphic modifications, they will recrystallize to polymorph modification 2 or polymorph modification 3. It depends on the polarity of using solvents. Also, if you do slow crystallization of solution of these nitrogen nitroxides, you can easily obtain these two polymorphs from polar solvent polymorph 2 from a non-polar solvent polymorph 3. These polymorphs have very different network of intramolecular contacts. So let's discuss them. Polymorphic modification 3 of Cyrhetren nitroxide derivatives has the same, almost the same structure with previous described manganese compound. Also, we have dimers that are connected in chains by hydrogen bonds. Polymorph modification 2 has also very similar dimers, but with much better pi-pi staking effect and with smaller distances between nitroxide groups. And these compounds, these dimers are connected in tetramer by short contact between nitroxide group and hydrogen atom of cyclopentadienyl cycle. And in case of polymorph 1, we have not observed any short contacts between nitroxide groups. They are much more than 5 angstrom, but for on these compounds we can observe quite short contacts between nitroxide group and carbon atoms of cyclopentadienyl rings. Magnetic properties of these compounds have shown that also for most of them we can observe antiferromagnetic exchange interactions, and for compound 3, they are almost the same like for manganese compound. You cannot maybe see it here, but I have shown for you both curves, and they show the perfect match that I have seen ever. So it was calculated exchange interactions in these dimers, and we can see that for compound 3 they are smaller than for compound 2, and also they have very good agreement with fitting value for compound for polymorph 3. It's also smaller than for polymorph 2. In case of polymorph 1, we have not any contact between nitroxide groups, and we expected only very small exchange interactions between these two molecules. Also, we can see here obviously, and calculated exchange interactions of this dimer only about 1 inverse centimeter, and the fitting values show maybe have shown very similar values. And also here you can see the results of fitting and for and calculated weight values both for rhenium and for manganese compound. You can see that they are very similar to each other. So,
And yeah, sorry, it's time to close more or less.
okay, so concerning the structure of rhenium nitroxide is also not very interesting from magnetic point of view. The distances between nitroxide groups are very big, and we can see only very small exchange interactions. Also, we obtained several complexes. What I would like to say that for manganese and for rhenium compounds, with manganese HPC2, we can observe very different structures. And in this case, I can say that Cyrhetren nitroxide-substituted ligand is much weaker than manganese, than Cymantren nitroxide-substituted ligand. And also we obtained very interesting molecular structure where we have 5 manganese nucleus, and this structure have not been observed previously in this ratio. Concerning the magnetic properties of this structure, they are also very interesting. We have only antiferromagnetic exchange interactions between radicals and between manganese centers in HFAC environment, but in spite of this, we have increasing of magnetic moment. So, summary. We obtained stable complexes. We studied them, but now we are only at the beginning of our big wave. We need to do functionalization to prepare something suitable for purpose of diagnostics, the increasing of solubility and for introducing affinity with target receptor. But the stability of these complexes is very promising approach for diagnostic, where the therapy with rhenium manganese 40 compounds could be combined with diagnostic by the magnetic resonance imaging using nitroxide radicals as contrast agent. So we published the rhenium part in this article. And also I would like to say a lot of thanks for all colleagues with whom I obtained this data and performed so nice study. So thank you for your attention.
Thank you very much, Kseniya. Do we have any questions? Well, I should not ask questions because you sent me this slide. So if there's no any questions, maybe you can ask Kseniya later in some private discussion room during the poster session or in the letter. And now let's make a pause for 12 minutes, actually quite short break, and then we get back to our last short section, and Professor Mikhail Kiskin will be a chairman of this last session. Thank you.